So what we're going to do here, and these are going to be the first lab we're going to do is we're going to let y'all check a diode. Everybody okay on how to check a diode? We still called it an ohm meter, but it has a diode scale, right? You understand that? And what the diode scale does, it actually shows you the voltage the ohm meter would have to put out to cause the current flow. So it's really, really neat. You can use an ohm meter, but ohm meters are looking for a real high ratio between forward bias and reverse bias. So my meter showed overload and it showed 1.2 meg when I forward biased it, right? So just about all your new digital meters has a diode scale. When digital meters first came out, they would not break over a diode. They didn't put out enough voltage to break over a diode. So we could not check diodes with a digital meter. I sure am glad that they added that capabilities as they evolved this thing. It's called a diode scale, but guys, you can check any p-in junction with that scale right there. So what we're going to do now is we're going to look at how do we take the diode and make it convert AC into DC. So what advantage does DC have over AC?
Storage.
We can store it, but we're not talking about it in this class. This class is called solid state devices. So what advantage, but you're exactly right. What's the other big advantage to DC? So undoubtedly I didn't put that out. It can be electronically controlled.
Okay, magnetically. No, it's storage. Okay,
So we can electronically control DC. So every electronic device operates off of DC. It might have an AC power supply, but it operates off of DC. So this right here, this guy right here, this is a power, we call this it's an AC to DC converter. We usually call these power supplies. What's this guy doing for me? On this side, I have what? AC. On this side, I have DC. So your TV has a power supply on it. Your microwave has a power supply on it. Most of your ovens have power. Most of your stoves have power. If it's got a digital readout up there, like most of them do now, it has a power supply in it, right? Because it has electronic timers and stuff like that. My coffee maker's got a display on it. I can set times and stuff to make it make coffee for me in the morning. So it's got a power supply in it, right? That's converting what? AC into DC. So what's one of the big, in this class, we're looking at this feature right here is that DC can be electronically controlled. So we got to come up with some method. So your car has an alternator in it. What do you think what does it put out? Alternator? So what's inside yours? It's got to be something in there that converts it to what? DC, because your car operates off of DC.
The alternator.
Alternator. So this is what we're going to look at here. How can we take AC and convert it into DC? And we're going to do that with diodes because diodes only let current flow in how many directions? One direction. Now you get it, don't you? AC flips, right? One direction. It'll kick. But what we can do is we can also steer it. It's really quick. So what we have is DC power supplies. So every electronic device is going to have a DC power supply somewhere, or it's going to operate off batteries. So that's another one that Brian brought up is that another major advantage that we can't do with AC that we can do with DC is we can store it. So our cell phones actually have batteries in them, right? This guy's got a battery in it, but I could take the battery completely out, and it's still gonna work because I have what button. Also, I got a DC power supply. So now if I turn off, if I unplug it, I'm gonna lose everything. So this guy right here. So this guy right here is running my computer now, right? I'm not using it to charge the battery. It's actually running the computer. On this side I have what? AC. Over this I have DC. Somewhere in there we're going to have a unit called a rectifier. A rectifier is a circuit that takes the AC and converts it originally into DC. So what we get out of a half-wave rectifier without filtering in, what we're going to do is we're going to get out one alternation and then we're going to block the other. And that's why it's called half-wave. So what we'll do is we'll get this out. It's going to be DC because it never changes direction. Now on full-wave rectifiers, what we're going to do is somehow we're going to steer the negative alternation or the positive alternation up to the top. So we're going to end up with this right here. So any DC power supply, now we're going to filter this out, right? You understand, because this will not run electronic devices. Electronic devices want some nice, pure, regulated DC. What do we mean by regulated DC? Well, we mean when I add or take loads away, the output voltage is going to stay fairly constant. There's no such thing as perfect regulation. It's just like the speed control on your car is regulated. But it's not perfect, right? You understand? It does not guarantee if you hit it on 80 that it's going to stay on exactly 80 all the time. In fact, your speedometer might say 80, but if you put a sensor on there, it might be going from 80.1 to 80.3. And then when you get past the limits of your regulator, it can't even do that, right? So if you start going up a hill, it might act when it starts shifting down, right? Eventually you're going to lose speed. And then when you go down a steep hill, you're going to actually exceed it because you're over the limits of the regulation, right? You understand that? So half waves are going to give us, this guy is going to give us a signal like that out of the rectifier. And full wave, somehow we're going to come up here and we're going to flop that sucker, we're going to flop the other polarity around. So if I create a negative power supply, then we're going to block the positives and allow the negatives to go through. And a positive power supply, we're going to block the negatives and let the positive come through. Everybody okay? This makes sense. So half wave has the advantage in that it's very, very cheap. Full waves have the advantage that it costs more money. But we get better DC. It's easier to filter out the noise. And we'll talk about that. Yeah, it's cheap. It's cheap. So these are used on low current demands because our filters, by the way, we'll look at this. They have to maintain the load. So half waves are usually used on low current demands, and your full waves are going to be used on your higher current demands. Well, what we're going to do is, let's say I had the ability to store a charge. So if I come over here on this thing and I unplug it, right now I'd go dead out off the bat, but when I unplug it, as soon as I unplug it, what happens to the battery? It starts what? Yeah, it picks up the load, but instantly, as soon as I unplug that thing, what happens to the voltage out of the battery and the current? It starts going down, right? Your batteries run down. Okay. So I could use a battery like your car battery, and that battery I would charge it up on the positive alternation, and then the battery would run the load between it, right? So a car on an alternator, your car could act as what we call a filter, so it's going to get rid of that. What we're going to use called the device, but batteries. The battery for this thing right here. If I was to buy a new battery, guess how much it costs? About $150 for this guy right here. My daughter-in-law just bought a new battery for her vehicle and paid almost $200 for that. So high capacity batteries cost a lot of money. So what we do is we use something that's very low capacity, right? You understand that? So what happens is we can charge it up, and then when we drop over here, what happens is it starts discharging, and then when it hits this side right here, it will charge it up again.
Yeah.
You can't see what I'm doing. Yeah. So what that means is if this was AC, my thing that I charge up would have to handle the load for 16.7 milliseconds. Over here, it would have to handle the load for 8.3 milliseconds. So that means automatically what I use to charge up over here on my full wave is going to take that time. Plus, when I look at this, when I try to get now the DC is going to be an average, right? You understand that? So which one would give me the highest average? Well, think about this. Over here, how many volts do I get right here? So over here, I might have, this might be 0, and this might be 1, 2, 3, 4, 5, 6, 7, 8, and then it would start, as soon as it hit peaks, it would go back down on the other side, and then this is going to be 0, 0, 0, 0, 0, 0. Up here, this is going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 8, and it's going to go 7, 6, 5, 4, 0, but we don't have all those zeros in there. Instantly, it starts going what? Up. So that means this guy right here would be, this guy here would be an average way up here, an average DC voltage up here. This guy right here is going to be an average DC voltage down here somewhere. So right off the bat, using full wave, my average DC is going to be higher. And the higher the voltage, the less current's required to produce the power, right? You understand that? Huh? Can handle more. So DC can handle more, can handle more current for the same size transformer, is what we're saying. So these we call full wave, and we have two types that we'll cover, called a full wave center tap, and then we have a full wave bridge. The half waves, you can see in a minute why it's so cheap. And we'll use I got to get my camera working to show y'all this. Full wave would get a higher average voltage out of it. Yeah, because if I was to take this and run it in a 1K resistor, I would get more current in 1K out of this than I would out of that, right? That makes sense. Huh?
So we okay right now. We thought it was gonna be a little bit more harder than what it is for the moment.
It's not, but
right now, we'll be okay.
Okay. So a DC power supply, this is the most common circuit. This is the most common electronic circuit. First AC and the DC voltage. So think about all the DC power supplies you have, even in your house, that you might not be able to hold in your hand. But so if you got a TV, it's got a watt in it. It's got a DC power supply. Right? If you've got a refrigerator that's got a digital readout on it, you've got a DC power supply. Right? If you got a microwave, all the microwaves I know of now, used to, we bought microwaves that had a knob on it. Now it's got all electronic. It's got a DC power supply. Anything that's electronic is going to have to, anything that's electronic that plugs into your power, into Alabama Power, it's got to have a DC power supply. If it's got batteries in it, if it's got rechargeable batteries, then you have a DC power supply that you hook up to it to charge the batteries, right? That makes sense? Like iPads and your cell and your smartphone. So what we do is power is the most often used circuit. So every electronic device.
So them little blocks that we charge our phone.
That's an AC to DC converter. In fact, if you look at it in that small print, it would say it's a 120 to 250 volts AC in, and it would say so many DC, but 5 volts because they charge off USB. USB puts out 5 volts. it would say 5 volts, and then it would come up and give you a current rating on it, if you look at it close enough. So that is that's a DC power supply. So all those little cubes you got that you charge up, that's the AC to DC power supply. So right now, if I was to cut this cord and measure the two, well, actually measure the two power leads on this thing, it would measure 5 volts. A rectifier, this is the actual circuitry that's converting the one, convert AC into what we call pulsating DC. Then what we're going to have to do is we're going to have to come in and we're going to try to filter that out and convert it into what we call unregulated DC. So what we're talking about is so a battery is unregulated. That means if you put a load across the battery, it's got nothing to compensate for the internal resistance of the battery. So right off the bat, as soon as you put a load across the battery, the voltage would drop down some. Because there's no such thing that has no resistance, right? You understand that? So that means a battery has internal resistance, and if you put current through resistance, then you're going to have a voltage drop. And that's why batteries get hot when you want you try to get a lot of current out of it, they get hot, right? You understand? Because you're putting what? You're putting current through resistance. So what we do is we use regulators. So what regulators do is that if the output voltage tries to drop down, we put more energy. We electronically put more energy in it to keep it at a current level. And we'll look at regulators. So unregulated unregulated DC power supplies means the output voltage would literally drop when you load it down. And when you unload it, it would do what? It would go up. So what we would end up, once we filter that out, is we're going to end up with unregulated DC. And there's a capacitor to rectifier and capacitor filter removes the pulses. Produces not a neat, it says a lot, a fairly smooth DC.
So regulated goes down, unregulated goes down, but once you disconnect it, it goes back.
But what regulated does, as long as it's just like your speed control, it's got an electronic circuit in there that looks at the output. If the output tries to drop down, then it adds more energy into it and causes the output to stay the same. Close to the same. There's no such thing as perfect regulation. So this is a regulated power supply. So it's got an electronic circuit in it. If I put a load across it, it's going to try to maintain that output voltage with the load, as long as you don't exceed the limit. So this guy over here is rated at 1 amp. And if I try to get 1 amp out of that power supply, then regulation is no longer guaranteed. The output voltage will literally start dropping down. The 5 volt supply is 5 amp supply. So this is a 5 amp, I'm sorry, this is a 3 amp supply. So, and these are rated, I don't know if there's a current on these. I know 5 volt regulator that's on this thing is rated at 5 amp. And this is the one they blow all the time. It's a 5 volt supply. So this guy's got the 5 volt, the 5 volt regulator is gone out of this. It's not gone, it's there. So I know right off the bat to fix this thing, all I gotta do is just replace that regulator and then it'll be back up and running. We have 2 devices we use as filters. The book only covers capacitors, but we also use devices called inductors. So we looked at capacitors a little bit, right? You understand that? So capacitors in a DC circuit acts like a real small chargeable. We charge them up. And then once we charge them up, then we run it into a load and they start discharging real fast. So this is what we get out of a half-wave rectifier. And this would be a positive. Okay. So this is the basic makeup of a lot of them. We start off with a rectifier. Then we're going to do what? Filter. And then we're going to have a special electronic device called a regulator. And what's that going to do? It's going to try to maintain a constant output even though the load is changing. Not even that. We say, what voltage does Alabama Power try to give us over here? Yeah, 120. What's the odds of that happening? 7 to 9, yeah. So this regulator is not only going to compensate for varying output loads, the regulator in a power supply actually takes care of changing input. if it's designed correctly, if the engineer designs it correctly. If the engineer creates a bunch of crap, then of course it's not going to work the way it's supposed to. So when we design this thing, we're going to try to design it around what? A change in input. Alabama Power says plus or minus 10%. So you could literally have anything 12 volts up and 12 volts down would still be considered legal. So that's what I would design around. I would design around what your power company guarantees, right? Understand? And if it gets out of those limits, it gets out of those limits. So what happens when the power fails? Everything in your house that's electronically controlled usually does what? Goes off. Because you've gone out of the limits of the power supply. It's really, really easy. Unless you got a backup power supply. So a regulator is a circuit that maintains an almost constant DC output voltage to the load with varied input voltage and varying load currents. But these are going to be within a certain range, right? You understand that? Yes or no? So as soon as we exceed those limits, then regulation is no longer guaranteed. So that's one of your power supplies. That's one of your specifications that you would have on a power supply is what it can give you. A regulator can consist of a single electronic device in the form of an integrated regulator or these discrete devices. Discrete means individual devices. So this guy uses electronic circuits. He uses these electronic circuits we call regulators. It's got fixed regulators in it. We got a plus and minus 12 volt regulator. We got a plus 5 volt regulator. And then we got a variable regulator, which is really neat because that means you can do what without the voltage. You can actually adjust it, which is what I'm running off now. Everybody okay? Unregulated DC power supplies is what we're going to look at right now. So this is the actual formula for the average value of an alternation. So, which looks very complex, but anytime we deal, so what we're dealing with is we're dealing with, so we know that AC is generated on a circle, right? Understand that? Okay. And we have this thing right here. What do we call this right here? The line that goes around the outside. Anybody know? Starts with a C.
Okay.
Now we call this line right here. It's got a name. So if I put a dot in the center right here, and then I draw a line through it, what's the name of that line? Diameter, right? And then 1/2 of it would be radius, and then this right here would be what we call the circumference. So what is pi? How do we come up with pi? Yeah, I know.
With the apples, with all that brown sugar.
Yeah,
You missing this slide on that.
really? Well, I'll put it up there. Yeah, sometimes these things don't quite get into sync. I'll make modifications and I forget to put them up there. So how do they come up with this 3.14159 and it keeps going on and on for infinity, right? And it never repeats. Normally we leave off at 3.14. How did they come up with 3.14? We take the diameter, we take the circumference of any circle, and we divide it by the diameter, and it will always come up and give us this thing called pi. So it is the ratio between the circumference of a circle, any circle, and divided by the diameter. That's where pi comes from. So if I'm going to deal with the circumference of a circle, then we're going to come up and we're going to use pi.
Circumference divided by the
Diameter always comes. The ratio of a circle is the ratio of the diameter and the circumference of the circle is a fixed value. So if we were to take a string and run it around the circumference, and then we were to measure the diameter, it would always come up to be 3.14 They had a little, I think it was like an 11-year-old kid that carried out pi to like 100 digits. Pi is a non-repetitive number. It never starts repeating, which is unbelievable. And every number that has ever been written is somewhere in pi. I learned that on the Person of Interest, Harold on Person of Interest. He was a genius. And he said that, and I said, you know, that's true. So your social security number is somewhere in pi, in consecutive digits. Your phone number is somewhere in pi. If I knew where it was, we'd be in trouble, right? So I could take any circle. So anytime we start dealing with the circumference of a circle, we're going to start dealing with pi. So what we're doing to calculate the average voltage is now we're on the circumference of the circle and we're not dealing with angles anymore, right? You understand that? So guys, this is it right here. This is the average. We call it, most people say 2V peak. This is V peak over pi. This is the average DC value of an alternation. Yeah, this will be on your formula sheet. Y'all forgot to remind me to give y'all the formula sheet up. Didn't y'all? Y'all supposed to do that? So we learn, this is the way a lot of books teach. They say, okay, the average value of this is 0.637. I don't like using that because now this guy right here is so much easier to remember. 2V peak over pi. I have that down. This 0.637 or 63.7% would be hard. You could use 0.637, but what's going to happen is you're going to vary it. Sometimes you'll use 0.637. Sometimes you'll use 1.414. Sometimes you'll use 2.82 to rearrange the formula. So 2V peak over pi works all the time. And that gives me the average value of an alternate, the average DC value of an alternate. So if I came over here, this guy right here gives me V peak, 2V peak over pi. This right here gives me a 0. What would be the average of a 2V peak over pi and a 0? So what's the average of 2? What's the average of 2 plus 0? I would come up here, I'd divide that by 2, and that would give me an average of 1, right? Everybody okay? So what we do for this one is we just use V peak over pi because the 2 is gone. It's averaged out total. So that means the average DC voltage I would get out of a half wave would be V peak over pi. What's that? Well, no, what we're doing is we're averaging this together. So what we're doing is we're averaging 2V peak over pi with 0. This is what I did over here, right? So if I do an average, what do? You add the two numbers together and then you divide it by the number that you have. So if I say 2 plus 0, and then I divide it by two numbers, it comes up and gives me an average of 1. So what that means is what happens is this 2, for this, it turns into a what? It turns into a 1, right? And it turns into V peak over pi. So the average DC for a half-wave rectifier is V peak over pi. And that thing calculates out perfect. If we was to use pi all the way out. So we'll hook this circuit up. And maybe I can get my camera going again so we can actually look at this on the oscilloscope. If not, we'll just come up here and look at it. And we can basically do this. So all I have to do to make a half-wave rectifier, guys, is this is all there is to a half-wave rectifier. So all we have is this guy right here. That's all there is to it. This right here being the low. the diode. So when my AC goes, when this goes negative, what would happen? This guy would fold reverse bias, which would cause zero current to flow. The resistor would drop no voltage. I get no work. Then during the positive alternation, the diode is forward biased. Then it would let the positive alternation come through. So I get 1/2 of the work, right? You understand? So one time we're getting 0 volts, the other time we're getting 2 V peak over pi. So we end up with V peak over pi. So y'all got y'all have y'all's lab book? Y'all got y'all's lab book in DC. So everybody's got a lab book, right? So we're gonna try to do labs next class. One lab that we're definitely gonna do is let y'all figure out how to check a diode out. You laughing at that? So average value of a half-wave output voltage, the value that would measure across with a DC motor, DC would be what? V peak over pi, or you could use 1/2 of 3 point, whatever it was. You could memorize, you could just number down. You could use it. So on your formula sheet, what I'm going to do is I'm going to use this. Use that one. Because the average of 6.28, 6.3, what is that? 6.37. If you divide that by 2, this is what you'd come up and get. Huh? Which one's he going to use? Yeah, and the problem is a lot of books teach you that, and they don't tell you how they come up with it. They just throw it out there and say 6.37. Yeah, the average value of I think that's even in the textbook for DC, or in AC, I think it is. So now you're trying to memorize fractions instead of just V peak over pi. So full weave would be V peak over pi times 2. So this is what I got. So we have a transformer in our triangle. And if we go all the way across it, we get 12.6 volts. We go between any side and the center tap, so it's the center tap transformer, and we should measure about 6.3 volts. Makes sense? Okay. What I'm doing is I've got my circuit hooked up to the common. They call it ground, by the way, guys, but it's not a ground. This trainer, this is a common. So it's not grounded. And I'll show you that when we look at the schematic. So I've got it going to one side of my diode. Got this going in here. Is this negative or is it positive? It's likely neither, right? Because it's what? They say. Good question. Good answer. And then I got my transformer right here to go into. So right now what this thing's doing is going to let the positive alternations come through, and it's going to block the negative alternations, right? So we come over and look at our oscilloscope. Now this is the big advantage of an oscilloscope, is an oscilloscope shows you what's there. Your meter is going to give you the average, right? Does that make sense? On this class, we're going to use an oscilloscope. If you had AC, then you probably need to team up with somebody that hadn't had AC, right? And y'all can help them with this thing right here. So the big advantage of an oscilloscope, a meter gives you an average, right? You understand that? Of course, if you got it on AC, it gives you that RMS value. you got it on DC, then it gives you the DC average of an alternate, not of an alternation, unfortunately, it gives you the DC average of a what? Of a sine wave. So right now, if we measure this, can y'all see what we got here? So I got it on 2 volts per division. I have my, and I got, guys, you don't have to say zero reference. So normally when we're dealing with DC, what we'll do is, see, this is my 0 volt reference right here for channel 1. I'll say it. We can set that anywhere we want to. On AC, we'll set it in the center. On DC, what we try to do is I use set my 0 volt reference down here at the bottom, and that way I can get more accuracy out of my measurement. Of course, it's over a little bit. So what voltage are we measuring? So I've got it on 1 volt per division now, so we're measuring 1, 2, 3, 4, 5, 6, 7 volts. Peak. So what should my average DC out? This is what I'm having problems with. I don't know what's going on with my meter. So what average DC work are we getting out of this thing right now? That'd be 7, that's DP, divided by 3.14, which is what we're going to use for pi. 2.22, so a little over 2 volts. Right? What happened to what?
You said the point was, what is BP? Yeah, 2 BP over pi.
Oh, no, that's for, full.
Okay, so that's 2 BP over pi. This is 0. So what we're doing is we're averaging 2 BP over pi and 0. So half wave, we drop the 2. Full wave, we use the 2. Half wave, we drop the 2. This is half wave. Why do we call it half wave? Because we're only getting 1 alternation, right? You understand? We're not getting 2 alternations. And of course, all I need to do to change the polarity of the waveform is all I need to do is just reverse the diode. Now, normally you wouldn't do this on an active circuit, but we only got 7 volts there, right? 2 volts. So now all of a sudden, when I hook this back up, now we have what? Now we have negative. Now my scope has gone out of sync. I'll have to think. So now we're getting 7 volts again, but now it's negative. So that's all we have to do to get a negative power supply is just flip the diodes around, right? Understand? So we have the ability to get a positive power supply or a negative power supply. And we use both of them, especially if I'm going to regenerate AC. So if I'm going to take DC and regenerate AC, then we're going to have to get a negative and positive voltage, right? You understand, to get AC. So that's what your car radio's got one of those in there. Because you can't put DC across the speaker. If you put DC across the speaker, it'll burn the speaker up, burn your radio up too. So your car radio is actually taking 12 volts or 14 volts, depending on if your car's running or not running, and converting it over to a plus and minus DC, and then they can electronically regenerate what? AC at whatever frequency we have, and that's all music is. It's just AC waveforms that's combined with each other. So I'll try to show y'all audio on this oscilloscope. I'll let y'all see what it actually looks like. It's very, very easy. So that means if I put my meter across this thing, I should measure a negative, around a negative 2 volts, right? And this is the problem I'm having. For some reason, my meter's not measuring what I expect. I don't know if it's the meter or what. But when I look across the diode, it's saying the diode is dropping the other part. So this is what I don't understand. I don't know what I've got wrong with it. Across the diode. So the diode is dropping the other alternation, right? It's dropping the positive alternation. So the negative alternation should be getting through. But when I take my meter and put it across the resistor, it's showing me this. And I don't know what I'm doing wrong. Anybody got a meter? Anybody bringing their meter? That's okay. This is 60 cycle, guys. We shouldn't be having any problem with the frequency response of the meter. So digital meters, one of the specifications on a digital meter is what the highest frequency they can measure without going haywire. And oscilloscope has that too. So notice this oscilloscope is rated at what? 25 megahertz. Which means if I try to measure a signal higher than 25 megahertz, then the reading it gets is not going to be right. This is an auto ranging meter. But I don't know what I'm doing wrong. Can y'all see anything I'm doing? So if you don't know, we don't know. Plus paging the same thing. So this is my meter. I got it across the resistor. It's measuring 0. So when I go across the diode, it measures what we're supposed to measure across the resistor. See that? But notice here it's positive because it's blocking the positive and it's letting the negative get through, right? Huh? Well, the diode is constantly switching between reverse to forward and reverse to forward for every alternation. So it's forward bias. Anytime it gets up above about 7/10 of a volt, it's going to let the negative alternation come through and block the positive. So that means it's letting the negative alternation come through. So I'm over here looking at the resistor with an oscilloscope. So the oscilloscope shows me what's there, right? You understand? So according to this, if I measure this with a meter, we should measure the average of this thing. If I put it on DC. And it's not. So it's measuring the positive alternation, okay, but it's not measuring this side. And then of course if I swap the diode around, so now we have what we call a positive power supply. Now I have to reset my 0, right? You probably think about it. So what we have to do is the oscilloscope is displaying pictures, kind of like your TV does. Used to on old TVs, we have what we call horizontal and vertical poles. And what you were doing with that, you'd adjust those into the TV was in sync with the camera, so the camera's taking pictures. We have to do the same thing with the oscilloscope. So right now what it is, it's out of sync. So right now the oscilloscope has no reference on where to start the trace and where to end it. So we have a circuit in there that we call a trigger, and you can actually see the trigger, see the white line. to do is just move that into the waveform. Now the scope is synchronized, and this synchronizes the oscilloscope with the signal it's trying to measure. Does that make sense? So if you come over here and you look at this thing and it's snaking all over the place, what that means is the scope is not synchronized with your signal. So right now I'm trying to synchronize it with something way up there. What does it do? That's what it does. Yeah, it's jumping all around, right? So what we need to do right off the bat is we need to, first of all, you select a channel that you're going to trigger on. So I'm going to bring up my trigger menu, and we've got this set up. This is dual channel stuff. So we got channel 1, we got channel 2. You synchronize your scope on. You can only trigger on. Normally we only trigger off one channel. So right up here, what we do is we select which channel we're going to trigger off of. And this scope comes with identifiers, which is really, really neat. So you can put these little rings around here. And then, of course, the color of the trace would be the color of the probe that you have measuring that. So if I bring up channel 2, it's going to be displayed as blue. And then we also put those rings out here on our. So what we used to do before they did digital scopes is we'd actually put tape on one of our probes. Because you got all these probes laying around. It's just like when you got 2 or 3 meters in a circuit, you forget what. And they're both black and red, you forget which lead belongs to what meters. So we're synchronized, and this is what we have, and this is what I can't really understand, is that if I've got this on my oscilloscope, why isn't my meter measuring that across my resistor? Because that's where I'm measuring that. And this might be the problem, that where we have our reference at. So it might have been where I was referencing my scope because of where I was referencing. So, yeah, I know why it's doing something. Okay, that was it. So it's where I was referencing my meter and where. So, let me check. So while we're going to put the common of the meter, we always want that pointing toward the bottom of the resistor. So what do we calculate? Around 2.2 volts. Okay, so right now, so that was it. So what happens is now I've got a positive supply because I've got my anode. So to determine if it's a positive supply or if it's a negative supply, you look and see which is pointing toward the source. So here the anode is pointing toward the source, so that means this right here is a positive supply. So if I come over here and look at my waveform, it looks a lot better now because I'm using the right common back up. So I was using the common on this, and it's isolated. So here's my positive waveform, right? We're measuring what? We're measuring 7 volts. Are we okay? Are we okay? Yes, no. Well, let's, because I got it on 2 volts per division. So 2, 4, right? 2, 4. Oh, now we're measuring about 8. Now we're measuring about 9 volts. So what would be? Is that right? 2, 4, 6, 8, and it's halfway in the middle, so that would be 9 volts. So what should we expect now? What? What'd you say? Let's get this correct.
You're gonna start it.
Well, we start right here where our zero reference is, right? On this line right here, so I've got it set on this line right here.
Oh, that's the lowest thing is.
Okay. Over there, 0,
Yeah, right.
4, 8.4 votes. So let's recalculate that. So 8.4 divided by pi divided by 3.1. Yeah, because each one of these would be worth 0.4. 2 votes per division. So what we have is we've got 5 divisions between each major division. So anytime I have a division, this right here would be worth 0.4, right? So about 2.4. So what do we calculate now? 2.67. And this is what we're measuring. Yeah, it's close enough, right? That's only 200 millivolts off of what we figured, what we thought it was going to be, and what our meter actually measured. Now, what I was doing wrong, I was using this guy right here.
Ground?
They call it common. It's not a ground, it's common. They call it ground, but it's common. So if I was to measure, if it was a ground, I could take an ohm meter and measure from here and measure to the stop on my power supply, and it should measure 0 ohms. So this meter is definitely, this guy's definitely. And then this transformer is totally isolated from this right here. So the only way you get ground through a transformer is if you put a ground on both sides, right? So this is why your house, you have a ground out on the power pole, and then if you go over there by your meter, they have a ground over there to reestablish ground once it goes to the transformer. Because power is sent through the transformer, not electrically, it's sent through there what? Magnetically. So we do what we call isolation transformers, where we deliberately run the AC through a transformer to get rid of the ground. Now the ground is no longer available, right? You understand? So what happened was, is I was using this over here, and this right here is this transformer, the secondary of the transformer is not referenced to that.
Which is the 0 and 6.3.
What's that? Yeah, so I had to use the Z, so I had to reference it to the 0, this 0 on the between the 6.3. And now everything works. Now what do I have to do to change it from a positive to a negative? It's the same on my DC meter. All I've got to do is what? Just reverse the diode. I don't keep unplugging it. And now we should measure about the same thing with my meter. But now instead of being positive, I'm going to keep my reference on 0. Now instead of being positive, so notice my scope, now it's alternation. So what I'm going to do is I'm going to come up here, change my 0 reference. I'll see my 0 reference, it's right here. So I'm turning the position control, and I get it up here. It's right there. And then it's snaking. Why is it snaking? Because we've lost our watt. Correct. I don't know why. And of course, this should
Would that be? I don't know.
yeah, it's telling me that it's telling me I've got the range of my trigger out of the display. So I get it way up here, and I keep turning it, trying to make it go higher. It can't go higher, right? So it's beeping every time I turn that little knob. So that's a good point. It should do the same when I get all the way down here and keep turning. Saying my trigger is out of range, right? Now, if we measure the time, so we got it on back set up to measure this. So what we have is we have it on 2.5 milliseconds per division. So each one of these would be worth 2.5 milliseconds, right? This one's a little hard. And you can measure time on the oscilloscope anywhere. So what we're going to do is we measure one cycle. So this is one, I'm sorry, this would be one cycle, the time it takes to repeat, right? So let me get this on the line. So normally what we do to measure time is we put something on the line. So I'm gonna use this reference right here, so it'll be 1, 2, 3, 4, 5, 6.248. 2.68. So 6.8, and multiply by this, and it's going to come up and give you 16, pretty close to 16.7 milliseconds. So wait, we got two options when we calculate this. Notice what I did a while ago, because I've been using the scope for a long time, is since I had it on 2 votes per division, I counted in what? I just counted in twos, right? So most of y'all can count in twos.
It said most of that.
Yeah, so both got to count. And then if I count in twos, I've got to get a 2 between this thing right here, and I've got 5 of them, so that means each minor division would be worth 0.4. Now another way you can do it, you can come on here. Oh, that's not me. What most people teach right off the bat is that by counting 1, that means each minor division would be worth a 0.2. Everybody understand that? Yes or no? So I can come over and I can say 1, 2, 3, 4.2. And then I can multiply that by the number of votes per division, and that would give me what it measures also. You understand that? Yes or no? So, go ahead. Do you really? So, this is the way they'll teach you out math. Count the number of divisions. Yeah, you count the number of divisions. But each minor division would be worth 0.2. Multiply it by these, right? Well, the problem we have here is this sucker's got 2.5 milliseconds. I can't count in 2.5 milliseconds, right? Now, if it was a 1 or a 5, so what I'm going to do is I'm going to line to line. I know each one of these is worth 0.2, and I'll go 1, 2, 3, 4, 5, 6, 0.4, 6, 8, right? So I'd say, okay, that would be how many? What I count? 1, 2, 3, 4, 5, 6, 0.8, and then I would multiply it by 2.5 milliseconds, and it should give you around 16. It's going to give you 16, but you know it. And it's going to be about, we know it's actually 16.6666 milliseconds. So making measurements on your scope is not extremely accurate because of the resolution of the scope, right? You understand that? But you get close enough so you can actually visualize what it is. So what do we get? About 17 milliseconds? And we know for a fact it's actually what? 16 points. What's that? About 17, yeah. And the problem is it's not exactly on A. So this is A. What I was going to do, guys, is I don't have one in here. So this is a capacitor, and it's polarized. So it's polarized. Okay. So let's change it back to a positive. Positive. So this is easier to see. So when we operate a capacitor in DC circuit, what is that? That's like a very small charger fast, right? This guy right here, we have that 7 volts. I'm going to make sure this has a
loads, so we're safe. Like, so, I just don't have my players on the I'm looking in here, yeah, I'm gonna make sure I put this in there right? So I'm gonna say the negatives, put it in here, across the plug. Find a slot. Watch what happens. Oh, there's voltage, it's unregulated. So you can actually see how it charges up to speed. You can actually see if it charges up below, it charges up to, so here's the road, and so we're filtering using a capacitor to filter out, but here's on the, sorry, here's the capacitor. What's gonna happen to our average, I want what's gonna happen to our average. Jumps up to almost 8 days. Almost. Down the filter. And what happens is what I'm gonna do is I'm gonna try to find an exit filter. And I'm gonna increase the current. So that doesn't.
Could you show us the actual breadboard?
Yeah.
So here's the actual breadboard. So notice I have my filter in parallel with the load. I made sure I honored polarity. Oops, not to make a short circuit there. So I've got the negative on the capacitor pointing towards the negative on the supply. And all I'm doing is just putting it on there and taking it off. So now it's halfway, now it's halfway rectified. Okay. And what I'm gonna do now is
We call it unregulated, which means the output varies with the load. So what I'm fixing to do is I'm fixing to come over here and we'll look at my scope, and all I'm going to do is put another resistor in parallel. I'm just going to touch it. And what do you notice? The ripple goes up, and I would look at my average voltage goes down. So this is what we mean by regulated. The actual unregulated, it means the actual output voltage varies with the load. So this is unloaded. This is loaded with a 1K. Here I'm going to put the resistor in parallel. And notice it drops down to, so this is what we mean by unregulated, right? So unregulated means I'm getting DC out. It's still not pretty DC, but it's actually DC now. So we call this unregulated DC, which means the output is going to do what? It's going to vary with load. If I take the 1K off, I mean, if I was to take just the 1K out, we get DC out. I mean, look at this. I'll have to do that another way. But what would happen? If I come over here and take the load out, we get pure DC now. But now we're not loading the capacitor at all, right? You understand? So this is really nice DC right here, right? As soon as I hook up a load, then all of a sudden my DC goes down, and we can actually see. We call this a ripple voltage, and it varies with load. So the less load I do, the capacitor don't have to run the load, right? So the capacitor's literally running the load during that amount of time. So it's just like a battery, but it discharges really fast. So if I loaded it too much, then our output would go way down, right? You understand that? But you can actually see the slope of the capacitor. You can actually see that the capacitor is running the load through this time right here. And what happens, when you charge on the next, So all we're doing now is looking at the ripple. You can actually see it charge the capacitor. Right here, the capacitor charges. Well, then as it goes down, the diode is reverse biased, right? You understand? Because now we got it charged up, so the diode cuts off. And what's happening now is the capacitor's running the load until when? Until the next alternation. So you can actually see. So this is still 16.7 milliseconds. So that means your capacitor's going to have to run the load for 16.7 milliseconds, 16.66 milliseconds. If it was full wave, it would only be running the load for about 8.3 milliseconds. So this is a DC power supply. This would be unfiltered. Sorry, disconnected the wrong thing. This would be unfiltered. Now what is that unfiltered out? Take that DC out, but it's very, very cheap, right? How many diodes to get halfway? One. So we have this, a 2-volt motor would run perfect off this. A DC motor would run perfect off this. A 2-volt light bulb would run perfect off this. It don't care that it's doing like this. A light bulb would average it out. Electronics will sit there and hum at you all the time because it's going to be cutting off 160 times a second. Okay, guys, this is where we're at. Try to bring your meter next class. Everybody's got their meter. Try to bring your lab book next class. And we'll definitely do a lab.